We spend almost all of our lives inside buildings, but we hardly ever stop to think about the incredible, hidden systems that are constantly working to keep us comfortable. Well, today, we're going to decode that secret language. We are pulling back the curtain on the invisible engineering that makes our modern lives possible.
Really think about that for a second. How is that even possible? It's not magic, I promise you. It's the result of this massive, incredibly complex system. Really, it's the lungs and the bloodstream of the entire building. We call it HVAC. And to really get it, you first have to learn to speak its language.
So here's our game plan. First, we're going to learn to speak the HVAC language, nail down some key terms. Then we'll peek inside an engineer's secret toolkit. After that, we'll see how everyone is playing by the rules. And finally, we'll explore your building's hidden world and see how all this stuff actually affects you.
All right, first things first. To understand any system, you've got to know the lingo. So let's start with a few basic definitions that engineers use all the time to describe the very spaces we're in right now.
Okay, first up is probably the one you're most familiar with, a conditioned space. This is your office, your home, most stores. And the key word here is and. It means the system can both heat you up when it's cold and, just as important, cool you down when it's hot. It's the whole shebang.
Now, slightly different is a heated space. And the name says it all, right? It's got mechanical heating only. So think about a big warehouse in a cold climate, or maybe a workshop in a garage. The goal here is just to keep things from freezing, but there's no AC for those scorching summer days. It's simpler, but perfect for what it needs to do.
And this one is absolutely critical. A ventilated space. You see, the main goal here isn't about temperature. It's about your health. Ventilation is all about bringing fresh outdoor air in to push the stale, yucky indoor air out. Now, that fresh air might be heated or cooled on its way in, but its number one job is just to keep the air you breathe fresh and clean. So how do all these systems actually make decisions? Well, a lot of it comes down to this really simple but kind of brilliant logic. A device is either normally open or normally closed. This is what it does automatically if the power ever goes out. Think about it for a safety system. If the power fails, would you want a smoke damper to fail open and let smoke spread, or fail closed to contain it? This simple design choice is a huge part of how engineers make sure systems fail in the safest way possible. Okay, now that we're speaking the language, let's take a look at the tools engineers actually use to put these systems together. And you'll see it goes from quick, back-of-the-napkin guesses all the way to some seriously complex math.
Right. Before an engineer gets lost in pages and pages of calculations, they almost always start here. A rule of thumb is just a quick and dirty estimate. It's based on years of experience, and it helps them get a ballpark idea of what a project is going to need right from the get-go.
And this is a perfect example. Let's say you're an engineer designing a basement in a city where it hits minus 10 degrees in the winter. You can just glance at this table and know, boom, you're going to lose about 2 BTUs of heat per hour for every single square foot. It's not the final answer, but it's an amazing starting point.
But let's be real, you can't build a massive skyscraper with just rules of thumb. For the final design, when every single detail matters, for efficiency, for cost, for safety, engineers have to break out the heavy-duty, complex calculations.
Whoa, okay, don't panic. You do not need to understand this formula. Seriously. We're just showing it to you so you can appreciate the insane level of detail that's involved. This specific equation, by the way, helps figure out how to convert a rectangular duct size into a round one. And trust me, every single piece of these systems has math like this behind it.
So, all that complicated math gets turned into actual physical hardware. You've got your ducts, which are basically the arteries carrying air all over the building. You've got piping, which are like the veins moving liquids like water or refrigerant. And then you have the fans and pumps. They're the heart of the whole operation, pushing everything exactly where it needs to go.
So engineers have the language, they've got the math, they've got the tools, but they can't just build whatever they feel like. Nope. They have to play by a very strict set of rules, a playbook written by major organizations to make sure everything is safe, efficient, and reliable. And these are the big ones. You've got ASHRAE, which sets global standards for air quality, and the ICC, which develops the building codes that are law in most places. These groups are the referees. They write the rulebooks that all designers have to follow, setting the absolute minimum requirements for everything you can imagine. Let's look at a real-world rule. An economizer is this cool device that just uses cool outside air to cool the building instead of firing up the AC. Well, as you can see here, the rules say you don't need one in a really hot place like Miami. Makes sense. But if you're in a more moderate climate, it's mandatory for bigger systems. Why? Because it saves a ridiculous amount of energy.
And these rules aren't just about saving energy, they're about saving lives. A fire damper is a metal door inside a duct that's designed to slam shut in a fire to stop it from spreading. But, and this is so important, in a system that's exhausting hazardous fumes, like from a science lab, you are not allowed to have one, because closing that damper would trap those dangerous fumes inside, making a terrible situation so much worse. That one rule shows you just how high the stakes are.
All right, let's bring this all home. We've learned the language, we've seen the tools, and we get the rules. So now let's look at how this hidden world is impacting you, right now, wherever you are.
Take a look at this number, 7. That comes straight from the ASHRAE rulebook. It means that for a standard office, the HVAC system is designed to deliver a bare minimum of 7 cubic feet of fresh outdoor air to you every single minute of the day. To put that in perspective, that's about the size of a microwave oven, filled with fresh air, delivered to your desk constantly.
And the rules also prevent waste. To make sure these systems are efficient, codes put a hard cap on how powerful the fan motor can be for the amount of air it moves. This number, 1.2 horsepower, is like a speed limit. It forces engineers to be clever and design really smart, low-friction systems that don't just gobble up electricity. So when you boil it all down, here's what it means. An HVAC system is so much more than just an air conditioner. It really is the building's respiratory system. It's the lungs and the bloodstream, breathing in fresh air, exhaling the old, and circulating health, safety, and comfort to every corner of the building, silently, all day long. So the next time you're inside and you feel that perfect cool breeze wash over you, I hope you see more than just a vent in the ceiling. I hope you'll see the language and the tools and the rules, an entire hidden world of engineering, all working together in perfect harmony just to keep you comfortable.